Well, hello everyone. So in order for you to prepare for next week's exam, I thought I would work out all of the questions from the practice midterm homework assignment. So here we go. I pulled it up on my laptop and on my iPad. And so the first question relates to converting moles of something into moles of something else. And so this is just really talking about if you have 1 mole of oxygen, how many of these would you have? And so the rule here is that if you have a mole of anything, it's equal to a mole of anything else. Even though, we're talking like oxygen is not the same as any of these other molecules, um, it's still, we're talking about the number of these substances. And so it's the same, they contain the same number of molecules. And so 1 mole of oxygen would be 1 mole of, what is this, acetic acid. Okay, so CH3COOH. Okay, so that's just a general rule. And I guess the same number of molecules, I guess a question on the actual exam may be a little more explicit and say, how many molecules of oxygen do you have? And so that would be Avogadro's number, right? So we would have this many molecules of oxygen as well as that many molecules of acetic acid, okay? For this question, the equation is balanced already. So this is a redox reaction, and it's balanced. I guess you can just kind of double check, do a quick double check. So we've got 2 manganese. How many carbons? I guess 10 carbons. 10 carbons. Okay, so everything looks balanced. And so it's saying if you have 1 mole of oxalic acid, and in case you don't know what that is, it says what it is. Okay, so you have 1 mole of that. And so it's asking then that reacts with how many moles of permanganate? Okay, so for this one, you just set up a little ratio. Okay, so we have oxalic acid to permanganate is 5:2. Okay, so I'm just looking at these balance coefficients. Okay, and so if we're told that we have 1 mole of the oxalic acid, then how many moles of the permanganate? So you just kind of cross multiply, or in other words, you would just multiply by 2/5. Okay, you divide by 5, multiply by 2. Okay, and so that would be 0.4. All right. This one is just about naming, and so I think pretty straightforward. Make sure you look at the PowerPoint slides for all the names of other kinds of acids, like iodous acid, all of those ones. But this one is just hydroiodic. So this one you have to balance and then do some calculations. And so balancing, I guess I would start with magnesium, so those are balanced as is. Then, since iron's by itself, I'll leave that for last. So let's go then oxygen. I see 3 there, so you're going to need a 3. And then that will change, you need a 3 there. And I guess that means you need a 2 in front of there. Okay, so let me double check. Yeah, so everything is balanced. And so now you're producing 15 grams of iron 3 oxide is the name of this, by the way, just as a review. Right, because the iron is formally a 3+ oxidation state. Okay. And so anyway, it doesn't have anything to do with the question, but FYI. And so if we have, we want to produce 15 grams, how many grams of magnesium oxide did we need? Okay, so again, this is going to use these ratios. So it's going to be a 1 to 3 ratio here. Okay, so our strategy is to first calculate moles of iron 3 oxide. Okay, so for that, we're going to have to look up the periodic table and there we go. So iron is 55.845. And we have 2 of them. And then oxygen, we can just say is 16.0. And we have 3 of them. Okay, so calculator. What was that again? So 3 times 55.845. And then 16 times 3. So that's 159.69 grams per mole. Okay, so then that's what you divide it by. Okay, so then we're going to go 15 divided by that. And that's 0.0939 moles. Okay, so that's moles of iron 3 oxide. For us to get moles of magnesium oxide, I have to multiply by 3, right, because it's a 1 to 3 ratio. So that times 3 is 0.282 moles. Okay, and then grams, we just have to multiply by whatever the molar mass of magnesium oxide is. So if we go back to the periodic table, magnesium is 24.305. And then let's go with 16.0 again. So it's 40.305. Grams per mole. And we're going to multiply that by 0.282. And we get 11.37. Okay, or 11.4, I guess, to the right number of sig figs. Okay, so again, the strategy was to first figure out moles for your iron 3 oxide, convert it to moles, and then grams of your magnesium oxide. Okay, this one, so a type of titration, and so this one you have to balance it as well first. So let's do calcium first, so that's a 3. Let's then look maybe for the phosphate, so we got 2 of those, so let's do a 2. And then maybe the hydrogens. So we've got how many on the other? On the left side, we've got 6, another 6, so 12 hydrogens. So then that means we need a 6 in front of there. And so let's see if that works. So now oxygens, we have 6 and 8, so 14. And then we've got 8 and 6. Yep. Okay, so balanced. All right, and now The red flag in these questions are if you are given a volume and molarity. You can then get moles from that. And so this would be 0.0150. Remember, capital M is moles per liter times 0.02500 liters. Okay, so that's 25 mils in terms of liters. Okay, so if you do that calculation, 0.015 times 0.025 is 3.75 times 10 to the minus 4 moles, and that is of calcium hydroxide. Okay, so we want to know phosphoric acid. Okay, so that's this. Okay, and we don't know this. And so for you to convert those moles to phosphoric acid moles, that's a 3:2 ratio. Okay, so we have to divide by 3, multiply by 2, or in other words, you multiply by 2/3. Okay, so let's do that. So times 2 divided by 3, and so that's 2.5 times 10 to the minus 4. And now that is moles of phosphoric acid. Okay, and so you're given the molarity of it, so 0.03. Okay, so the way you can figure out volume then is set up a little ratio. So if you have 0.03, that many moles in 1,000 mils, okay, or in 1 liter, then how many mils in this 2.5 times 10 to the minus 4? Okay, so you set that up, and hopefully we end up with 8.33. So you do 2.5 times 10 to the minus 4 times 1,000 divided by, what was it? 0.03. And we get 8.3 mils. Okay, which is the right answer. All right, this one, I guess just a naming. So again, just look at the PowerPoint slides for all of the names for these different acids. Strong electrolytes, this is again kind of a definition. That means 100% dissociated. And so, in other words, they're completely broken apart into ions. And so this is a salt, so a metal with a nonmetal, and so those will break up into sodium plus, Cl minus. Same with that. And then these are all strong acids. Okay, so remember the strong acids are going to be HCl, HBr, HI, and then nitric, sulfuric, really the first proton of that, and perchlorate. Okay, so just those 6 are strong. In this case, acids, but also you could say they're strong electrolytes. And so any other acid, like HF, for instance, that would be a weak electrolyte, okay, because it's only partially dissociated. Non-electrolytes are things that do not break apart at all, so 0% dissociated, and those will be organic compounds, essentially. So I think there's a question coming up later, but like sugar, other types of organic compounds, compounds that contain predominantly carbon, oxygen, nitrogen, hydrogens, those like methane, for instance, or those kinds of things, those will not be dissociated at all. Okay. This is a tricky question. How many cations are in 10 grams of sodium phosphate? And so why it's kind of tricky is because you have to first know what the formula for this is. And so sodium phosphate, if you have sodium and phosphate, you have to remember phosphate has a 3- charge. And so that means this formula is this. Okay. And then if you have 10 grams, you have to convert it into moles first. Okay, so sodium is about, we can say 22.99. And we have 3 of them. Phosphorus is 30.974, and we have 1 of them. And then we'll just say 16.0, and then we have 4 of those. So the molar mass for Na3PO4 is 22.99 times 3. And then we had 16 times 4. And what do we have? Phosphorus, 30.974. So that's 163.944. And the units are, again, grams per mole. Okay, so that's what we divide this by. Grams per mole. Okay, so then 10 divided by that is 0.061, we'll say, 0.061 moles. Okay, and so this is asking how many. So we're going to have to go from moles to number of something, so we're going to multiply by Avogadro's number. Okay, so if we multiply this by Avogadro's, 6.02 e to the 23rd, we get 3.67 times 10 to the 22. Okay, so that's one of the answers. Why is that not the right answer? And so here it's noting that for each one of these, so for this whole compound, that's how many we have. We have 3.67 times 10 to the 22nd of Na3PO4 units. Okay, but this is asking how many cations. So for this compound, we have 3 times the number of sodium pluses as we do PO4 minuses, right? Whoops. So this would break apart, in other words, into this. Okay, so we have 3 of those. So in other words, we have to multiply this by 3. Okay, which is actually that answer. Okay, so 3.67 times 10 to the 22. Now if we do times 3, that's the 1.1 times 10 to the 23rd. Okay, so in other words, you have 3 times the number of sodium cations than you do the whole compound. Okay. This one, how many grams of calcium chloride are needed to produce 10 grams of potassium chloride? And so you have 10.0 grams. How many grams of this? Okay, so again, our usual step is to figure out from grams to moles. And so potassium is 39.1, we'll just say. Okay, so 39.1 and 35.45 for chlorine. So 35.45 plus 39.1, 74.55. And that's grams per mole. So if we do 10 grams, that, so 0.134 moles of KCl. Okay, so we want to know calcium chloride, so it's a 2-to-1 ratio. Okay, so you just divide by 2 in this case. Okay, so 0.134 divided by 2 is 0.067 moles of calcium chloride. Okay, and then for grams, we just need to multiply by the molar mass of calcium chloride. So calcium is 40.078. Is that right? Yeah, 40.078. So this is calcium chloride. And then our 35.45 times 2. And that's 110.978. And again, the units for that are grams per mole. Okay, and so you just multiply those out, and that's 7.44 grams. Okay, or that answer. Okay, so for this next question, it's a lot of moving parts in it, and so let's just break it down here. So you're told you have 0.2 molar of this and an excess of that. So this is the limiting reagent, in other words. And you're going to produce 2.75 grams of the iron 3 sulfide, but the percent yield is only 65%. And so the theoretical yield is really 2.75 grams divided by 0.65. Divided by 0.65, so 4.23. Okay, so that is how many grams are theoretically possible, but you're told you only made 2.75 grams. Okay, so that's kind of the trick in the question. And so now this is what we want to calculate moles and then convert it to moles of our reactant. Okay, so therefore moles of Fe2S3 would be 4.23 grams divided by its molar mass. And so we've got 2 irons, iron 55.845, and there's 2 of those. And then sulfur is around 32, 32.06. Wrong one. And we have 3 of them. 2 times 55.85. And then 32.1 times 3, so that's 208. Okay, or 4.23 divided by that. So we get 0.0203 moles, and that's of our Fe2S3. Okay, so now I want to know moles of this reactant, and so that is a 1 to 2. Okay, and so you're going to multiply it by 2. Running out of room here, but 0.04, I guess I can do that one. 0.0406 moles of the FeCl3. Okay, and then you're told that you have 0.200 moles for every 1,000 mils. If I have 0.0406 moles, how many mils is that? Okay, so it's really 0.0406 divided by 1,000, or times 1,000 divided by 0.2. So that times 1,000 divided by 0.2 is 203.4. Oops. 203 mils. Okay, so kind of a tricky question, really, just from this step there, just realizing that that's how many grams that are theoretically possible. So that's what we use to calculate the question. Okay, here, how many oxygen atoms are in 3 grams of this? And so first thing we have to do is convert grams to moles. Okay, so 3.00 grams. And this is going to be a doozy here. So sodium, we can say, is 22.99. And there are 2 of them. Oxygen, and there are 7. And then chromium, 51.996. And there are 2 of those. Okay, so 22.99 times 2, we have 16 times 7, and then 51.996 times 2. So that's 261.97. Okay, so 261.97. So if we do that for moles, so we're going to do 3 divided by that is 0.0115. Moles. Okay, so this is asking how many, so that means Avogadro's number. So if we multiply by 6.02 times 10 to the 23rd, let's do that. Gives you 6.89 times 10 to the 21. Okay, and that is an answer. It's the wrong answer because this is, you have this many units. Okay, so you have that many units of sodium dichromate. It's asking for how many oxygen atoms. Okay, and there are 7 times, right? There's 7 oxygen atoms per one of these whole things. And so you just have to multiply it by 7. Okay, so that whole thing times 7, that gives you 4.82 times 10 to the 22. Okay, so this whole thing is that. Okay, so again, look in the compound. So if we were to ask how many chromium atoms are in there, you would multiply this whole thing by 2, right? Because there's only 2 chromiums in that whole compound. Okay, so this question is no calculation, finally, here. We're mixing methanol and water, and so this is recognizing that it is a non-electrolyte. Okay, so 0% dissociation, so it's going to stay intact as well as water. Okay, so it's not going to break apart into ions. Water isn't either. Okay, so both of these will remain intact. In which one is it not -2, the oxidation state? So this one, you're assuming it's -2 because aluminum will be a 3+, and that gives you a total of 6, right? Because you have 2 aluminums. So that means that this whole other side has to be -6. And if you divide it by 3, then each of them are -2. Okay, this one, magnesium, all it can be is +2. So that means it has to be -2. Lithium, all it can be is +1. And if there's 2 of them, then that means you have +2, so that means that has to be -2. For this one, though, sodium has to be +1. If there are 2, then that means that the whole left side of the compound is +2. But we have 2 oxygens. So then each of the oxygens then have to be -1. Right? So in other words, if I write it out like this, right, if this whole side over here is +2, this whole other side has to be -2, but there are 2 oxygens, then each of them have to be -1 each. Okay, so that's another exception to the rule. Most of the time you can assume that oxygen will be -2. The products between the reaction, those reactions with these salts, so it is a double displacement, so the silver is going to steal the bromine and potassium is going to steal the nitrate. Okay, so just those products. Okay, and this next question, this is a more visual kind of a question about limiting reagents. And so in this one, if we just kind of write out what these are, so A2 are the unshaded, so we have 4 of those on the reactant side, and it's reacting with 1, 2, 3, 4, so 6 of the B's to form. We've got 4 B's left over, and I guess we call it A4Bs. We have 2 of those that are formed. Okay, so since we've got B's left over, then the A2 has to be the limiting reagent. So it kind of boils down to these 2. Now to figure out which is the overall reaction, we can first, get rid of 4 B's from either side. Okay, so we have a 2B there. And then we can divide everything through by 2 that's left, right? So that's a 2, and then we've got a 1 and a 1. And so that works out to this one, right? 2 A2s plus B gives you an A4B. Okay? This, for you to know if it is oxidation reduction, again, just look if you are going between an element and then it goes to a compound, then it has to be redox. Okay, so that's the easiest way to figure that out. And again, here you're going compound back to element. This is involving an acid and a base, so it's an acid-base neutralization where you get a salt and water as your products. This is related to activity series, so remember, the higher up it is, the more easily they are oxidized. Okay, so that tells you that potassium is oxidized before tin is. And so looking at these different varieties here, this is saying that, for instance, I guess none of these other ones really make sense. Aluminum, this is saying that aluminum is going to be reduced and iron is going to be oxidized, but it's the opposite way in the activity series. This one is saying that aluminum will be oxidized and tin will be oxidized, so that's not going to happen. This one is saying that potassium would be reduced and that would be oxidized, so you would go to like an iron 3 on there, but that's not even in the chart, so that doesn't apply. So this one says that you will go potassium to potassium ion, okay, and the tin would be reduced. Okay, and so then you're just looking for which is higher in the series. Potassium is, and so that means that it would be preferentially oxidized. Oh, great. And so balancing redox. Okay, so here we go. The steps are to break them up into half reactions. So you've got the iron species and the oxygen ones. Okay, now we balance everything other than oxygens, hydrogens. So that, and then I guess the oxygen one, there's nothing else. And then we look at balancing oxygens by adding water. So we're going to have to add 3 waters to this side. And that means we need 6 H pluses. In this one, we're going to have to add a water over here. And that means 2 H pluses over there. Okay, so now everything's mass balanced. We have to do charge balancing. This one, the top one, the right side is a +6 and the left side is neutral. Okay, and so that means we're going to have to add 6 electrons over here. Okay, so now both sides will be neutral. On this side we've got a +2 over here, and then this is neutral. And so we're going to have to add 2 electrons over here. Okay, so now both sides are neutral. Okay, so now to add these up, we're going to have to multiply this whole thing by 3 so that the electrons can cancel. So if I use my little eraser here, that means that we have 6 electrons. Six protons, a 3, 3, and 3. Okay, so electrons cancel, and now we just write whatever is left. I guess in this case, the protons cancel too, actually. And the waters. Wow, so that makes it pretty easy. So we've got 2 irons. Plus 3 ozones goes to Fe2O3 plus 3O2. Okay, so it's said in a basic solution In this case, since the protons canceled from both sides, we don't have any H pluses, so we don't have to add any OH minuses. And so this is it. Okay, so it's asking what are the coefficients in front of iron and ozone? It's 2 and 3. Okay, so we are done. So this is actually one example. It's kind of weird that in both acidic and basic, it's going to be the same thing. Okay. Another fun redox here. So that's nitrate goes to NO, and then this one is the copper goes to copper 2. Okay, so everything is balanced. So let's do water. So we're going to need another 2 waters there. And so that means 4 protons. And this one, nothing is needed. So the top one, this whole side, you have 4 minus 1, so that's going to be a plus 3 overall. This is neutral. So we're going to have to add 3 electrons over here. On this side, this is neutral, whereas this is plus 2. So we're going to have to add 2 electrons over here. Okay, so then we're going to have to multiply this one by 3, this one by 2. Okay, so let's do that. So you're going to have, I'll just cross it out this time. So we're going to have 6, 8, 2, 2, 4. And then this one is going to be a 3, 3, and 6. Okay, so the electrons are gone. And so what we end up with is 8 H pluses plus 2 nitrates plus 3 coppers goes to 2 NO plus 4 waters plus 3 copper 2 pluses. Okay, so I guess in the above they didn't include the protons and water. It's just asking what is the nitrate and the copper. And so here as well, it's a 2 and a 3. Okay. All right, another graphic illustration of balancing. And so in this case, A are unshaded and B. So we've got, again, A2, and we have 3 of them. Reacts with 1, 2, 3, 4, 5, 6 B's. And then over there we've got 1, 2, 3, 4, 5, 6 AB's. Okay, so here we can just divide everything through by 3. Okay, so we end up with 1 A2 reacts with 2 B's to give you 2 AB's. Okay. This is a molarity question. So concentration, that will always mean, most of the time, especially in this chapter, it will capital M. And so we want to know moles per liter. And so once you have grams, chances are you're going to have to calculate moles. So let's do that. So 10.0 grams divided by whatever iron 3 chloride. Okay, so that's iron 55.85, and then you've got chlorine, I just blanked on, 35.45. And you have 3 of them. So 35.45 times 3 plus 55.85. So it's 162.2. So divided So 10 divided by that is 0.0617 moles, and you have that volume of your solution, so 0.275 liters, in other words. So you just divide that by 0.275. So that's 0.224 capital M, okay, or moles per liter. Okay, when you see the word diluted, that tells you that you're going to have to use this one. M1V1, M2V2. So we have 65 mils of a 12 molar, 65 mils. It's diluted, so now we've got, we want to know M2. And its volume is 150 mils. Okay, so you can, I could have done this one in terms of liters. Okay, it doesn't really matter as long as both sides are the same thing. Okay, in this case, I decided to convert them both to milliliters. Okay, so it's really just going to be 12 times 65 divided by 150. So that's 5.2. Okay. And then a empirical formula. So if you're given percentages, you can convert those to grams if you assume you have 100 grams of sample. Okay, so in other words, you have 49.97 grams of carbon, 10.51 grams of hydrogen, and 39.52 grams of fluorine. Then you divide by their atomic masses, and fluorine was at 19, yeah, we'll just say 19.0. Okay, this one will, 49.97 divided by 12.0. Whoop. Is 4.16, 10.51 divided by 1.01 is 10.41. Too many sig figs, I know. It should be, I guess, 10.4. And then 39.52 divided by 19 is 2.08. Okay, so those are moles for each of those. So now the strategy is divide by the smallest, everything through by the smallest to get the ratios here. Okay, so that one is easy. This one is also pretty easy. And then 10.41 divided by 2.08. That's, yeah, I guess exactly as well. Okay, so our ratio here is C2H5F1. Okay, or you just leave the 1 off. Okay. What is the mass of that many molecules of ammonia? So again, remember this little chart. Okay, moles in the middle, then you've got grams, and then number. To get away from moles, we are multiplying by something. To get back to moles, we're dividing by something. In this case, this is Avogadro's number between the number of something in moles. And between grams and moles, it's the molecular weight or molar mass. Oops. Okay, so for this one, if we have that many molecules, then we have to divide by Avogadro's number first. Divided by 6.02 times 10 to the 23rd. 8.5. So that's 0.141 moles. Okay, and then you multiply, so we're here now. So we've gone from here to here, but we want to know grams, so we're going to have to multiply by the molar mass of ammonia. So that's 14 for nitrogen and another 3, so that's 17 grams per mole. So that's 2.4 grams. Okay, so molar mass of this, you're just going to add up everything from the periodic table. So cobalt is 58.9, and you have one of them. You have 14, which is nitrogen, and you have 2 of them. And 16 is oxygen, and you have 6 of them. So 58.9, whoops, wrong one. And then we had, what do we have? We had 14 times 2 and 16 times 6. So 182.9 or 183. Okay, molar mass of hydrogen gas. This is kind of a trick question. This will always be an answer. Remember, hydrogen gas is diatomic, just like if it were to say nitrogen gas, etc. So remember the ones that are, every time you say its name, it has to be diatomic. It's hydrogen, and then let me show you on the periodic table. So it's hydrogen, and then it's nitrogen, oxygen, fluorine, chlorine, bromine, iodine. So the little 7, I guess I can't write on the periodic table here, but yeah, it's really these ones. If I go back. So hydrogen, and then it's nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Okay. So 1, 2, 3, 4, 5, 6, 7, and then it forms a little 7 for you. Okay. What is the oxidation half reaction? So that would be the metal that goes to its plus state. So something that is increasing its oxidation state is oxidation.